Welcome to Biostatistics for Non-Statisticians. We would like to explain the CONSORT extension to cluster randomized clinical trials. Let us begin. In the usual design of cluster randomized trials, there are two types of randomized units. In one, we assign the intervention. The other is nested within the first, but here we evaluate the outcome. We will call them, respectively, units of intervention and units of inference. In the most typical example, we assign the intervention to health centres with the goal of knowing the effect on patients. Other common names are community trials or randomized group trials. Let's see an example of what a cluster randomized trial is and one of what is not. If we want to prevent unwanted teenage pregnancies and assign the intervention to some schools, we are looking at a cluster randomized trial. In the other example, we have a second opinion trial that seeks to lower the proportion of caesarean sections in different health centres where this response is directly measured. Here, both the intervention unit and the inference unit coincide in the health centre, and thus is not a cluster trial. Its only peculiarity was that its statistical unit was not made up of patients, but instead of health centres. This example, taken from the CONSORT extension to cluster trials, shows that 25 and 27 centres were assigned to the intervention and control, resulting in 172 and 156 patients in each group, approximately 6 per centre. In this flow chart of the 2012 document, the centres were 122 and 124, but in total, there were about 40,000 women in each arm. Under the usual statistical approach, each unit provides independent information. It adds 100% new information. In contrast, in a cluster trial, the patients in each group share certain common information, which must be taken into account in the analysis. This is because the usual calculation would provide results that are erroneously too narrow and too precise. The traditional confidence intervals would also be too narrow, and they would not have the desired coverage, usually 95%. To consider this, we have two statistical measures. First, there is the intra-group correlation, which measures the information shared by the members of each group. Second, we have the design effect. This indicates by how much we have to multiply the variance obtained in order to obtain the correct coverage. This table, taken from the CONSORT extension to cluster trials, shows that the shared variance depends on the chosen response, which is approximately 1% for cholesterol, 10% for weight, and 5% for diet. We define the intra-cluster correlation coefficient as the proportion of variability shared among the members of the same cluster with respect to the total variability. And here we have the formula for the design effect. As we can see, it depends 1. on the number of cases per cluster, that is, on the number of cases with repeated information. This is already provided by the others from the same group. And 2. based on the correlation. The effect also depends on the degree of shared information. In the example above, the design effect is almost 2 for weight, a big increase of 100%. But it is inflated only 7% for cholesterol. Thus, the implications of this formula are 1. Since ICC is modelled in terms of variances, it cannot be negative. DE is greater than or equal to 1. 2. Typical ICC values are in the range between 0.001 and 0.10. 3. If the correlation is null, ICC is equal to 0, DE is equal to 1. The variance of the estimator does not increase. 4. DE also depends on N, the number of cases per group. 5. DE can multiply by 2 the variance of the estimator, even for a low ICC, 0.05, if the number of cases per centre is 21. 6. If DE is greater than 1, ignoring it erroneously causes an increase in alpha risk and potency. 7. The degrees of freedom for estimating ICC depends on the number of G groups rather than the number of GN cases. 8. The ICC estimate is usually very poor. It is better to rely on conservative premise about its value. For example, ICC is equal to 0.10. 9. If the number of G groups is small, example 20, it is not appropriate to rely on the balance of randomization based on asymptomatic results. It is better to stratify or minimize, which also increases efficiency if the correlation between the response and the adjustment criteria in randomization is 0.5 or greater. Cluster trials may present additional risks of bias. 1. Masking may be impossible. Patients and investigators will know the intervention that is practiced in a certain cluster. 2. Unlike traditional individually randomized designs, allocation concealment may be impossible in cluster trials because, first, the intervention is assigned, and second, the patients are recruited, thus reverting to the usual procedure. 3. Therefore, both recruiter and volunteer can cause selection bias. In summary, CONSORT's extension to cluster design requires specifying 1. Both random units in the flowchart. 2. The reasons for making a cluster design. 3. The intra-class correlation and the design effect. 4. Implications for analysis and rationale of sample size. And 5. The 15 subsections of the summary. And that's all for today. Well, no. One final tip. Practice. As a team, check if an article that you find interesting follows the recommendations of the CONSORT extension to cluster designs.